There's a frequency pulsing through the Earth right now that shouldn't exist at this intensity, and it's been screaming for days. The Schumann resonance, our planet's electromagnetic heartbeat, typically hums along at a steady 7.83 Hz, a rhythm as predictable as the tides. But in January 2026, monitoring stations across the globe are recording something unprecedented. Sustained spikes in the 20 Hz range with a sharpness that mirrors the exact signature detected 96 hours before the Turkey-Syria earthquake killed over 50,000 people. The mathematics are unsettling. The timing is uncanny. And if the pattern holds, we're standing inside a critical window where something catastrophic might be preparing to unfold beneath our feet. Stay with me, because what the data reveals about the coming days will fundamentally change how you think about the ground beneath you. Subscribe and follow along as the electromagnetic data continues streaming in from monitoring stations across the globe. Because what unfolds over the coming days will either confirm that these Schumann resonance spikes are just atmospheric noise, or reveal that we've been missing critical connections between Earth's electromagnetic field and the stresses building in the crust. This isn't about predicting the next major earthquake with absolute certainty. It's about recognizing that the patterns appearing in January 2026 mirror signatures we've seen before catastrophic events. Something is happening to the electromagnetic field that wraps around our planet like an invisible skin, and the instruments that measure it are showing readings that make scientists pause mid-sentence. Right now, in January of 2026, monitoring stations across the globe are detecting a sustained spike in what we call the Schumann resonance, and if history has any predictive power at all, we might be standing in the shadow of something catastrophic. The Schumann resonance is not some fringe concept dreamed up by conspiracy theorists. It's a real, measurable phenomenon first predicted by physicist Winfried Otto Schumann in 1952 and confirmed experimentally in the 1960s. Think of it as the planet's natural electromagnetic heartbeat, a frequency that pulses through the cavity between Earth's surface and the ionosphere, driven primarily by the thousands of lightning strikes that crack across our atmosphere every single second. The fundamental frequency sits at approximately 7.83 Hz, with harmonic overtones stacking up at roughly 14, 20, 26, and 33 Hz. These frequencies have remained relatively stable for as long as we've been measuring them, creating a kind of baseline hum that defines Earth's electromagnetic signature. But stability is not what we're seeing right now. Monitoring networks that track these frequencies have detected something unusual, something that breaks the pattern. The third harmonic mode, oscillating around 20 Hz, has been ringing louder and longer than typical atmospheric conditions would suggest. We're not talking about a brief fluctuation lasting minutes or even hours. These elevated readings have persisted, creating what some observers describe as a sustained electromagnetic event that refuses to dissipate into the background noise. The question that hangs in the air, whispered in research forums and shouted across social media, is simple and terrifying. What does it mean? To understand why anyone cares about wiggles on a spectrogram, you need to know about the strange and contentious field of seismoelectromagnetics. For decades, scientists have documented odd electromagnetic phenomena occurring before, during, and after major earthquakes. Ground-based sensors have picked up unusual electrical currents. Satellites have detected ionospheric disturbances over regions that later experienced massive seismic events. Radio receivers have captured strange signals in the very low frequency range hours or days before the Earth split open. The Turkey-Syria earthquake of February 6, 2023, a magnitude 7.8 disaster that killed over 50,000 people, was preceded by electromagnetic anomalies detected roughly 96 hours in advance by independent monitoring networks. Those anomalies looked eerily similar to what some observers claim to be seeing right now. Now, before you start packing an earthquake survival kit based on frequency charts, it's crucial to understand that mainstream seismology does not accept electromagnetic precursors as reliable predictive tools. The United States Geological Survey, the gold standard in earthquake science, has consistently stated that no validated method exists for predicting earthquakes with useful precision. The correlations between electromagnetic anomalies and seismic events are intriguing, statistically suggestive in some studies, but far from conclusive. The problem is signal-to-noise ratio. Earth's electromagnetic environment is a chaotic soup of influences ranging from solar wind, buffeting the magnetosphere, to ionospheric storms, to simple equipment malfunction. Picking out a genuine earthquake precursor from this mess is like trying to hear a whisper in a thunderstorm. Yet the speculation continues, and right now, it's focused on a specific window of time. Based on the 96-hour pattern allegedly observed before the Turkey-Syria quakes, some analysts have circled January 20th through 23rd, 2026, as a critical period. The math is simple if you accept the premise. If the anomaly was detected around January 16th or 17th, count forward 4 days, and you land in a zone where, statistically speaking, something could happen. Could, might, possibly. The language here matters because we're operating in the realm of educated guesswork dressed up in scientific terminology. The regions under speculative watch read like a geography lesson in tectonic instability. Central Asia, specifically the so-called stans, Kyrgyzstan, Uzbekistan, Tajikistan, sits atop one of the most geologically complex zones on Earth. This is where the Indian plate is still grinding northward into the Eurasian plate, crumpling the crust into the Himalayas, the Pamirs, the Tian Shan. The forces involved are almost incomprehensible. Entire mountain ranges are being built millimeter by millimeter, year by year, and all that compression has to release somewhere, sometime. These regions experience earthquakes regularly, most small, some devastating. A magnitude 7 or higher event in this area would not be geologically surprising. It would just be tragic. Then there's Cascadia, the subduction zone that runs from Northern California up through Oregon, Washington, and into British Columbia. This is where the Juan de Fuca plate is sliding beneath North America, locked in a silent struggle that has been building stress for over 300 years. The last time Cascadia fully ruptured was January 26th, 1700, producing an estimated magnitude 9 earthquake and a tsunami that hit Japan. The interval between megaquakes here is typically between 200 and 500 years, which means we are statistically overdue, though overdue in geological terms is a fuzzy concept spanning decades or centuries, not days. Still, Cascadia remains one of the most significant seismic threats to North America. A ticking time bomb that exists in a state of perpetual could go off any moment for the next century or two. Japan, of course, needs no introduction to seismic terror. Sitting at the intersection of 4 tectonic plates, the island nation experiences more earthquakes than almost anywhere else on Earth. The Great East Japan earthquake of March 11th, 2011, magnitude 9.1, killed nearly 20,000 people and triggered the Fukushima nuclear disaster. Japan's seismic monitoring is the most sophisticated in the world, and if electromagnetic precursors had any validated predictive power, the Japanese would have weaponized them by now. They haven't, which tells you something about the reliability of the method. But there's another element to this story, one that veers from geology into astronomy and brings with it a whole different flavor of speculation. On December 19th, 2025, just weeks ago, an interstellar object designated 3I Atlas made its closest approach to Earth at approximately 1.8 astronomical units, or about 167 million miles. This is not close in any meaningful sense. The Moon is only about 240,000 miles away for comparison, but 3I Atlas is special because it's only the 3rd confirmed interstellar object ever detected passing through our solar system. A cosmic wanderer that originated somewhere beyond the Sun's gravitational influence, perhaps expelled from another star system entirely. Its trajectory, its composition, Its very existence opens questions about the nature of interstellar space and what travels through it. Some online communities have latched onto the timing, an interstellar object passing through the inner solar system, electromagnetic anomalies on Earth, a potential major earthquake window. The human mind is extraordinarily good at finding patterns, even when the patterns are coincidental static. This is where legitimate science ends and narrative begins, where we move from measurement to mythology. There is no known physical mechanism by which a small icy body nearly 200 million miles away could influence Earth's electromagnetic cavity or trigger seismic activity. Gravity? Negligible at that distance. Electromagnetic influence? Comets don't generate meaningful magnetic fields. Yet the timing is curious enough to fuel discussion, debate, and more than a little fear. The spectrograms circulating online show what looks like structure in the noise. Hyperbola-shaped signals that rise and fall in frequency over time, creating visual patterns that our brains want to interpret as meaningful. Are they? Or are we staring at digital pareidolia, seeing faces in clouds, messages in static? The scientists who study Schumann resonance will tell you that the cavity mode structure is complex, influenced by 100 variables, and that transient features appear all the time without corresponding to anything terrestrial, let alone extraterrestrial. Still, the question lingers. What if Earth isn't just cracking under tectonic stress? What if the cosmos itself is whispering secrets through the electromagnetic spectrum, and we're only beginning to develop the instruments and the insight to hear them? What if the boundary between Earth science and space science is far more porous than we ever imagined, and events separated by millions of miles are connected by physics we don't yet fully understand? The clock is running. January 20th is days away. Monitoring stations continue to record. Scientists continue to debate. And somewhere, perhaps beneath the mountains of Central Asia or locked beneath the Pacific seafloor, stresses are building that care nothing for our interpretations, our fears, or our instruments. When the Earth decides to move, it moves. The only question is whether we're listening to the right signals or chasing ghosts in the machine. The numbers don't lie, but they also don't tell the whole truth without interpretation, and that's where things get complicated. When you're looking at Schumann resonance data, you're examining a spectrum of electromagnetic frequencies that oscillate within the Earth ionosphere cavity, and the fundamental frequency at 7.83 Hz is just the beginning. The harmonic modes stack up mathematically, each one a multiple of the fundamental, creating a series of resonant peaks that should, under normal circumstances, follow predictable patterns based on cavity geometry and ionospheric conductivity. The first mode sits around 7.83 Hz. The second mode appears near 14.1 Hz. The third mode clusters around 20.3 Hz. Fourth mode, 26.3 Hz. And so on, climbing into the higher frequencies where the signals get weaker and noisier. What observers have been reporting over the past several days is not an increase in the fundamental frequency, which would be truly bizarre and would suggest something fundamentally wrong with either the planet or the measurement equipment. Instead, they're seeing an unusually strong and sustained signal in the third mode, that 20 Hz range, persisting far longer than typical thunderstorm-driven fluctuations would explain. Lightning is the primary driver of Schumann resonance. Every time electrical discharge rips through the atmosphere somewhere on Earth, it pumps energy into the cavity, exciting these resonant modes. But lightning is transient, scattered, random. The resonance signature of global lightning activity creates a kind of baseline noise level that fluctuates, but doesn't typically sustain sharp peaks for extended periods unless something is continuously feeding energy into the system. The concept of Q factor comes into play here, and it's worth explaining because it's central to the claims being made. Q factor, or quality factor, is a measure of how sharp and well-defined a resonant peak is. A high Q means the resonance is strong, narrow, and sustained, indicating that energy is being efficiently stored in the resonant cavity without quickly dissipating. A low Q means the signal is broad, weak, and quickly damped out by losses in the system. In the context of Schumann resonance, a high Q factor in a particular mode could suggest that something is driving that mode preferentially, pumping energy into it in a way that sustains the oscillation longer than random atmospheric noise would allow. Now, mainstream Schumann resonance research doesn't typically talk about Q factor thresholds for predicting earthquakes because, frankly, no such validated thresholds exist. The field of geophysics has not established a causal link between Q factor spikes and seismic events. But the speculation goes like this. If stressed rock deep in the Earth's crust generates electromagnetic emissions through piezoelectric effects or other mechanisms, those emissions could, in theory, couple into the Schumann resonance cavity, creating detectable signatures in the frequency spectrum. A sustained, high Q signal in a specific mode might indicate a continuous source of electromagnetic energy, and if that source is tectonic stress building toward a rupture, then the signal could be a precursor. Could be, hypothetically. If a lot of poorly understood physics lines up just right, the spectrograms tell a visual story that's more compelling than dry numbers. When you look at a typical Schumann resonance spectrogram, you see horizontal bands at the expected mode frequencies, fluctuating in intensity as global thunderstorm activity ebbs and flows. Sometimes you see transient features, little bursts of energy that spike and fade. What some observers claim to be seeing now are structured patterns, particularly hyperbola-shaped traces that sweep across the spectrogram over time. These hyperbolic shapes are not random. They suggest a source that is moving or changing in some systematic way, creating a Doppler-like effect in the observed frequency. The question is, what kind of source produces this signature? One explanation is ionospheric disturbances. The ionosphere is not a static shell. It's a dynamic plasma influenced by solar radiation, geomagnetic activity, atmospheric waves propagating up from below, and a host of other factors. A traveling ionospheric disturbance could create a moving perturbation in the cavity properties, which might manifest as a hyperbolic trace on a spectrogram. This is a known phenomenon. Scientists who study space weather and ionospheric physics see these kinds of signatures regularly and attribute them to atmospheric dynamics, not seismic precursors. Another explanation, the one that excites the earthquake prediction enthusiasts, is that the hyperbolic traces represent electromagnetic emissions from regions of tectonic stress. The theory proposes that as rock deforms under enormous pressure deep underground, piezoelectric crystals, like quartz, generate electrical currents. These currents could propagate through the Earth's crust, couple into the atmosphere, and influence the ionosphere, creating detectable electromagnetic signatures. The hyperbolic shape would then reflect the spatial and temporal evolution of the stress field as it builds toward rupture. It's a neat idea. The problem is proving it. Piezoelectricity in rock is real. You can take a piece of quartz, squeeze it in a lab, and measure a voltage. Scaling that up to crustal scale processes is where the physics gets murky. The Earth's crust is not a clean crystalline lattice. It's a heterogeneous mess of different rock types, temperatures, pressures, fluids, fractures. The electromagnetic emissions that might be generated by tectonic stress would have to propagate through this mess, reach the surface, couple into the atmosphere, and make it up to ionospheric heights without being completely swamped by noise from thunderstorms, solar wind, human activity, and 1,000 other sources. The signal-to-noise problem is enormous. And then, there's the timing correlation with 3I Atlas, which is where things drift from speculative geophysics into the realm of cosmic coincidence. The interstellar object made its closest approach to the Sun on December 14th, 2025, and its closest approach to Earth on December 19th. Some online observers have noted that unusual Schumann resonance activity seemed to pick up around that time, leading to speculation that the comet's passage might have triggered or influenced electromagnetic conditions on Earth. The mainstream scientific response to this idea is a polite cough and a change of subject. Comets are dirty snowballs made of ice and rock. They don't generate powerful electromagnetic fields. They don't emit radiation capable of penetrating Earth's magnetosphere in meaningful ways. At one point, 8 astronomical units. The gravitational influence on Earth is negligible, far weaker than the gravitational tug of planets in our own solar system that we orbit alongside every day without noticing. But let's entertain the speculation for a moment, not because it's scientifically credible, but because it illustrates how pattern-seeking minds can construct narratives from coincidence. Suppose, purely hypothetically, that 3I Atlas carried with it some unknown electromagnetic property, some quirk of interstellar chemistry or solar wind interaction that created a transient disturbance in Earth's space environment. Suppose this disturbance somehow coupled into the ionosphere and, cascading down through atmospheric layers, influenced the Schumann resonance cavity. And suppose this happened to coincide with a period of building tectonic stress in multiple regions around the globe. The correlation would be striking. It would also be meaningless without a physical mechanism to connect the dots. Scientists are deeply aware of the human tendency to find patterns in noise. Our brains evolved to detect predators in the underbrush, to hear footsteps behind us, to see threats before they materialize. This hypersensitivity to patterns is a survival advantage, but it also makes us prone to false positives, seeing agency and causation where none exists. The technical term is apophenia, the tendency to perceive meaningful connections between unrelated things. Spectrograms are particularly vulnerable to this because they're visual, and our visual cortex is exceptionally good at finding structure. We see faces in clouds, animals in ink blots, and apparently earthquake precursors in electromagnetic noise. The skeptical position, the one held by the majority of working geophysicists, is that what we're seeing is likely a combination of normal Schumann resonance variability, ionospheric disturbances driven by space weather, and measurement artifacts amplified by selective attention and confirmation bias. The Earth's electromagnetic environment is always changing, always noisy, always producing features that look anomalous if you stare at them long enough. Without a validated physical model, without controlled experiments, without reproducible predictions that can be tested and verified, we're just telling ourselves stories about wiggles on a screen. But here's the uncomfortable truth. Absence of proof is not proof of absence. Just because we haven't validated a mechanism doesn't mean the mechanism doesn't exist. Science advances by taking anomalies seriously, by investigating the unexplained, by remaining open to the possibility that our current models are incomplete. Maybe there is something happening in the electromagnetic spectrum that correlates with seismic activity, something we haven't figured out how to measure properly or interpret correctly. Maybe the signal is real, buried in the noise, waiting for better instruments or better analysis or the right catastrophe to prove its significance in retrospect. The data is weird, the timing is suspicious, the correlations are intriguing, and the question that haunts every honest scientist looking at this is whether we're witnessing the early warning signs of something catastrophic or just chasing ghosts through the static. The next few days might tell us which. Or they might tell us nothing at all, and we'll be left exactly where we started, staring at spectrograms and wondering what, if anything, they mean. The scientific establishment has a complicated relationship with earthquake prediction, and that relationship is mostly defined by failure, disappointment, and public mistrust born from overpromised breakthroughs that never materialized. Mainstream seismology, as represented by institutions like the United States Geological Survey, the Seismological Society of America, and university research departments around the world, maintains a clear and consistent position. Earthquake prediction is not currently possible with any useful degree of accuracy. You can forecast probability over long timescales, saying that a region has a 30% chance of experiencing a magnitude 7 earthquake in the next 30 years, but you cannot predict that an earthquake will occur on a specific date at a specific location with anything approaching certainty. This position is not born from pessimism or lack of trying. Seismologists have spent decades searching for reliable precursors, measurable changes in the environment that consistently appear before earthquakes and could serve as warning signs. They've looked at everything: radon gas emissions, groundwater level changes, animal behavior, electromagnetic signals, ionospheric disturbances, thermal anomalies detected by satellites, patterns in foreshock sequences. Some of these phenomena do appear before some earthquakes, but the critical word is some. The patterns are not consistent, not reliable, not predictive in a way that would allow you to evacuate a city based on the data. The field of seismo-electromagnetics exists within this frustrating landscape. Researchers have documented electromagnetic anomalies associated with earthquakes for over a century. The 1965 Matsushiro earthquake swarm in Japan produced magnetic field variations that were measured and published. The 1989 Loma Prieta earthquake in California was preceded by unusual ultra-low frequency electromagnetic emissions detected by multiple instruments. The devastating 1999 Izmit earthquake in Turkey showed electromagnetic precursors in retrospective analysis. Case after case, study after study, the correlations pile up, suggestive but never quite definitive. The problem is reproducibility and false positives. For every electromagnetic anomaly that preceded an earthquake, there are dozens or hundreds of anomalies that led to nothing. For every earthquake that had a measurable precursor, there are major quakes that struck with no warning at all. Statistically, you cannot build a predictive model on data this noisy. Science demands reproducibility, and earthquake precursors simply don't reproduce reliably enough to be trusted. Yet, there are respected researchers, people with PhDs and publication records, who continue to argue that electromagnetic precursors are real and deserve serious investigation. They point to satellite data showing ionospheric anomalies over earthquake zones days before major events. They reference ground-based measurements of ultra-low frequency signals that spike before ruptures. They propose physical mechanisms involving rock stress, piezoelectric effects, and electromagnetic coupling between the lithosphere and ionosphere. Their work gets published in peer-reviewed journals, presented at conferences, debated in the scientific community. It has not convinced the mainstream, but it has not been entirely dismissed either. The contrarian position, distinct from mainstream skepticism, comes from communities that embrace alternative frameworks for understanding Earth and cosmic phenomena. The electric universe theory is one such framework, proposing that electromagnetic forces, rather than gravity alone, play a dominant role in shaping planetary and stellar behavior. Adherents of this view see Schumann resonance anomalies as evidence of Earth's electromagnetic connection to larger cosmic currents, possibly influenced by solar activity, galactic magnetic fields, or other interplanetary phenomena. This perspective is not accepted by mainstream physics, which has a very well-tested understanding of how gravity, electromagnetism, and nuclear forces operate at planetary and cosmic scales. But the appeal of the electric universe framework is understandable. It offers explanatory power for phenomena that mainstream science struggles to address, and it provides a narrative where Earth is not an isolated rock floating in space, but a node in an interconnected electromagnetic web spanning the solar system and beyond. When you view the planet through this lens, correlations between Schumann resonance spikes and interstellar object transits don't seem absurd. They seem expected, even predicted. The challenge is distinguishing between genuine alternative science and pseudoscience. Genuine alternative approaches propose testable hypotheses, make predictions, and adjust their models based on evidence. Pseudoscience wraps itself in scientific language, but resists falsification, cherry-picks data, and dismisses contradictory evidence as part of a conspiracy or establishment bias. The line can be blurry, and honest researchers can disagree about which side of that line a given idea falls on. One popular claim circulating in fringe earthquake prediction communities is that Schumann resonance fluctuations directly affect human consciousness, mood, and even health. The idea is that because our brains operate using electrical signals and produce their own electromagnetic fields, changes in Earth's electromagnetic environment could influence neural activity. There is no credible scientific evidence supporting this claim. Studies attempting to link Schumann resonance variations to human physiology have failed to produce reproducible results. What does exist is a lot of anecdotal reporting, people claiming they feel different when the resonance spikes, which tells us more about the power of suggestion and the human need to find meaning in our experiences than it does about electromagnetic effects on the brain. The media's role in amplifying these narratives cannot be ignored. Sensational headlines attract clicks. Earthquake warning, electromagnetic anomaly detected gets far more attention than electromagnetic fluctuation observed, cause unknown, probably nothing. Social media algorithms reward engagement, and fear and mystery engage far more effectively than caution and nuance. The result is a feedback loop where speculative ideas get amplified, spread, and eventually treated as established fact by communities that don't have the scientific literacy to critically evaluate the claims. Yet, there's a deeper issue here, one that goes beyond media sensationalism and touches on the nature of scientific authority. Science is often presented as a monolithic entity that speaks with one voice, but that's not how it actually works. Science is a messy, contentious process where researchers disagree, where paradigms shift, where today's fringe idea occasionally becomes tomorrow's accepted theory. The tectonic plate theory itself was once considered fringe, ridiculed by establishment geologists who couldn't conceive of continents drifting across the planet. The discovery of ball lightning, the confirmation of rogue waves, the detection of gravitational waves, all were dismissed or doubted before overwhelming evidence forced acceptance. So when someone says, "Scientists don't believe this," the question becomes, which scientists? All of them? Most of them? The loudest ones? And does their disbelief constitute proof that the idea is wrong, or just proof that the evidence isn't yet compelling enough to shift the paradigm? These are uncomfortable questions for people who want clear answers, and they're precisely the questions that keep contrarian researchers motivated. The honest position, the one that respects both the value of skepticism and the possibility of discovery, is to acknowledge that we don't know everything about earthquake processes and electromagnetic phenomena. We have models, some very good, that explain most of what we observe. We also have anomalies, outliers, strange correlations that don't fit neatly into the models. Maybe those anomalies are noise. Maybe they're clues. The only way to find out is to keep measuring, keep analyzing, keep questioning both the data and our interpretations. If a major earthquake does occur in the coming days, will it validate the electromagnetic precursor hypothesis? Not necessarily. Even a perfect correlation between the anomaly and a seismic event wouldn't prove causation without a physical mechanism. And if no earthquake occurs, will it disprove the hypothesis? Also not necessarily, because the proponents can always argue that the anomaly indicated risk, not certainty, and that we got lucky this time. This is the frustrating nature of probabilistic predictions. They're unfalsifiable in any single instance. What we're left with is uncertainty dressed up in data, speculation clothed in scientific language, and a planet that keeps its secrets buried kilometers deep, where no instrument can directly observe the stresses building in the dark. The Earth will do what the Earth does, indifferent to our theories, our fears, and our desperate need to predict the unpredictable. And we'll keep watching the spectrograms, hoping that somewhere in the noise is a signal we can finally understand. The physics of earthquake generation is reasonably well understood at a basic level. Tectonic plates move, stress builds, friction holds, and eventually something gives way in a violent release of elastic strain energy. What's less well understood is everything else, the complex cascade of processes that might precede that rupture, the electromagnetic and chemical and thermal signatures that might leak into the environment as stress accumulates, and whether any of those signatures could be detected reliably enough to constitute a warning. One hypothesis that has attracted attention from researchers is the piezoelectric effect in quartz-bearing rocks. Piezoelectricity is a well-established phenomenon where certain crystalline materials generate an electric charge when subjected to mechanical stress. Quartz is abundant in Earth's crust and is strongly piezoelectric. The idea is that as tectonic stress increases, enormous forces compress quartz crystals throughout a volume of rock, generating electrical currents that could propagate through the crust and potentially couple into the atmosphere and ionosphere. Laboratory experiments have demonstrated that stressed rock samples produce measurable electrical signals, lending credibility to the basic physics. Scaling this up to predict earthquakes is where the problems emerge. The crust is heterogeneous, fractured, saturated with fluids that can short-circuit electrical currents. The electromagnetic signals generated by stressed rock would have to travel through this electrically messy environment, reach the surface, propagate through the atmosphere, and influence the ionosphere in a detectable way. Each step involves losses, distortions, and competing signals from other sources. Thunderstorms, industrial activity, power lines, solar-wind interactions. All of these produce electromagnetic noise that dwarfs any potential tectonic signal. Extracting a genuine earthquake precursor from this electromagnetic chaos requires either an incredibly strong signal or incredibly sophisticated analysis techniques. The lithosphere-atmosphere-ionosphere coupling model, often abbreviated as LAIC, proposes a multi-step chain of interactions that could link crustal stress to ionospheric anomalies. The sequence goes something like this. Stressed rock releases radon gas from fractures. Radon ionizes the lower atmosphere, creating regions of altered conductivity. These conductivity changes affect the global atmospheric electric circuit. Atmospheric electric fields couple into the ionosphere via various mechanisms, including atmospheric gravity waves and electromagnetic induction. The ionosphere responds by developing anomalies in electron density, temperature, and other parameters. Satellite instruments can detect these ionospheric anomalies, and if they correlate with subsequent earthquakes, you potentially have a remote sensing method for earthquake precursors. Some compelling case studies exist. Before the magnitude 9.0 Tohoku earthquake in Japan on March 11, 2011, satellites detected ionospheric electron density anomalies over the rupture zone several days in advance. Similar anomalies were observed before the magnitude 7.9 Wenchuan earthquake in China on May 12, 2008. The data is intriguing, but again, the critical question is whether these anomalies are consistent enough and specific enough to be predictive, rather than just interesting coincidences that we notice in retrospect. Alternative explanations for Schumann resonance shifts have nothing to do with earthquakes and everything to do with space weather. The ionosphere is constantly buffeted by solar wind, the stream of charged particles flowing outward from the sun. When the solar wind is particularly strong, or when coronal mass ejections slam into Earth's magnetosphere, the ionosphere undergoes dramatic changes. Conductivity increases, electron density spikes, and the Schumann resonance cavity properties change accordingly. These space weather events are frequent, well documented, and completely unrelated to seismic activity. Distinguishing between ionospheric disturbances caused by solar activity and those potentially caused by tectonic stress is an enormous analytical challenge. The online speculation circles have latched onto the 3i Atlas timing. weaving narratives that connect the interstellar object's passage to Earth's electromagnetic anomalies. The reasoning goes, this object traveled through interstellar space, potentially carrying with it magnetic field configurations or particle environments different from those typical in our solar system. As it interacted with the solar wind and traversed the inner solar system, it could have created perturbations in the heliospheric magnetic field. These perturbations might have reached Earth and influenced our magnetosphere and ionosphere, and this influence could, somehow, manifest as Schumann resonance anomalies. This is creative storytelling, but it lacks a plausible physical mechanism. The magnetic fields associated with comets are weak and localized. The interstellar magnetic field that 3I Atlas might have carried with it would be negligible at interplanetary distances. The solar wind itself is a far stronger influence, and Earth's magnetosphere is specifically structured to deflect most solar wind particles. An icy body nearly 200 million miles away simply doesn't have the electromagnetic or gravitational oomph to meaningfully affect Earth's electromagnetic environment. The correlation is coincidental timing, nothing more. Yet there's an irresistible appeal to cosmic narratives, to the idea that events on Earth are connected to the wider universe in ways we don't yet understand. What if there is some unknown interaction, some subtle coupling between interstellar magnetic fields and planetary electromagnetic environments? What if the passage of certain types of objects through the solar system does create measurable signatures in Earth's ionosphere, not through direct electromagnetic influence, but through some indirect mechanism we haven't yet identified? This is where speculation becomes imagination, where science fiction creeps into the discussion, dressed up in what-if scenarios. The history of science is full of phenomena that were dismissed as impossible before being proven real. Meteorites were considered folklore until samples were analyzed. Continental drift was ridiculed until seafloor spreading was documented. Ball lightning remains poorly understood despite countless eyewitness accounts and occasional photographic evidence. The point is not that every speculative idea deserves equal credence, but that remaining dogmatically certain about what is and isn't possible can blind us to genuine discoveries. Open questions remain in Schumann resonance physics. Researchers still don't fully understand what drives the amplitude variations in different modes. The relationship between global lightning activity and resonance strength is statistically clear, but mechanistically complex. Higher order modes behave in ways that current models don't entirely predict. There are hints in the data that something more complicated is happening, some interaction between the cavity resonance and ionospheric dynamics that our simplified models don't capture. Fringe theories have emerged to fill these knowledge gaps, some more plausible than others. Geocosmic resonance theories propose that Earth's electromagnetic field is coupled to solar and even galactic magnetic fields, creating a nested hierarchy of resonant systems that influence each other. Proponents point to correlations between solar activity cycles and seismic activity, though these correlations are weak and contested. The idea that galactic cosmic rays could influence cloud formation and climate has some peer-reviewed support, though the effect size is debated. Extending this to seismic triggering is where most geophysicists draw the line, seeing no credible mechanism by which cosmic rays or galactic magnetic fields could significantly alter crustal stress. The challenge in evaluating these ideas is that absence of evidence is not the same as evidence of absence, but it's also not licensed to believe anything. Science progresses by proposing hypotheses, testing them, and discarding those that fail the test. Many earthquake precursor hypotheses have been tested and failed. That doesn't mean all possible mechanisms have been tested, and it doesn't mean that with better instruments and better analysis techniques, we might not find something genuine. But it does mean that extraordinary claims require extraordinary evidence. And so far, the evidence for electromagnetic earthquake prediction remains stubbornly ordinary, intriguing, suggestive, but not conclusive. If the Earth does crack open in the coming days, If a magnitude 7 or 8 earthquake rips through Central Asia or the Pacific Northwest, the question will be whether this event was foreseeable from the electromagnetic data. Even if it was, even if the correlation is perfect, we'll still be left asking whether the next anomaly predicts the next earthquake, or whether we just got lucky once and mistook luck for insight. The only way to answer that question is through time, through repeated observations, through building a statistical case that can't be explained away by coincidence. Until then, we're left in the uncomfortable space between knowledge and ignorance, watching the data and wondering what it means. The electromagnetic environment of Earth is not a closed system, isolated and self-contained like a laboratory experiment. Our planet sits embedded in the solar wind, that constant outward flow of charged particles streaming from the sun at speeds ranging from 300 to 800 kilometers per second. This plasma carries with it the sun's magnetic field, creating a complex and dynamic structure called the interplanetary magnetic field that pervades the solar system and interacts with every planetary magnetosphere it encounters. Earth's magnetosphere is the shield that stands between us and this cosmic barrage, a bubble of magnetic field lines that deflects most of the solar wind around us, protecting the atmosphere and surface from direct bombardment by high-energy particles. But the interaction is not simple deflection. When the solar wind encounters Earth's magnetic field, it compresses the dayside magnetosphere and stretches the nightside into a long magnetotail, extending millions of kilometers downstream. Variations in solar wind pressure, changes in the interplanetary magnetic field orientation, and especially the arrival of coronal mass ejections, massive eruptions of plasma from the sun's corona, can cause dramatic disturbances in the magnetosphere. These geomagnetic storms drive currents in the ionosphere, create auroral displays at high latitudes, and can disrupt satellite operations, radio communications, and power grids. They also affect the Schumann resonance. The ionosphere, that electrically conductive layer of the atmosphere between roughly 60 and 1,000 kilometers altitude, forms the upper boundary of the Schumann resonance cavity. Its conductivity depends on the density of free electrons, which in turn depends on solar ultraviolet radiation during the day and residual ionization at night. When a geomagnetic storm hits, the ionosphere's electron density can increase dramatically, changing its conductivity and thus altering the resonant properties of the Earth ionosphere cavity. Studies have documented Schumann resonance frequency shifts and amplitude changes correlated with geomagnetic activity, demonstrating that space weather directly influences what we measure on the ground. This creates an interpretive nightmare for anyone trying to use Schumann resonance data to predict earthquakes. How do you separate ionospheric disturbances caused by solar activity from potential precursory signals generated by tectonic stress? Solar wind conditions are monitored by spacecraft, and geomagnetic indices are published in real time. So in principle, you could filter out known space weather effects from your earthquake precursor analysis. In practice, the coupling between space weather and the ionosphere is complex and not perfectly predictable, leaving residual uncertainty even after accounting for known solar influences. Interstellar influences, if they exist at all, occupy an even more speculative domain. The solar system moves through the local interstellar medium, a tenuous gas with a density of about 0.3 atoms per cubic centimeter, threaded with magnetic fields of a few microgauss strength. This is an extraordinarily weak environment compared to the solar wind, and mainstream astrophysics holds that interstellar magnetic fields have negligible direct influence on Earth's magnetosphere. The heliosphere, the bubble carved out by the solar wind, extends roughly 100 astronomical units from the Sun and effectively shields the inner solar system from most interstellar influences. Yet there are phenomena we don't fully understand. Galactic cosmic rays, high-energy particles accelerated by supernovae and other violent cosmic events, do penetrate the heliosphere and reach Earth. Their flux varies with solar activity in an inverse relationship. When the Sun is active and the heliosphere is inflated, cosmic ray flux decreases. When the sun is quiet, more cosmic rays get through. Some researchers have proposed that cosmic ray variations could influence cloud formation and thus climate, though the mechanism is debated and the effect size appears small. Extending this logic to seismic triggering requires imagining that cosmic rays somehow modulate tectonic stress or trigger earthquakes in already stressed regions, a hypothesis that lacks both theoretical foundation and empirical support. Artificial intelligence is emerging as a powerful tool in analyzing the massive datasets generated by electromagnetic monitoring networks, seismic arrays, and space weather instruments. Machine learning algorithms excel at finding patterns in high-dimensional data, patterns that human analysts might miss or dismiss as noise. Researchers are beginning to apply neural networks and other AI techniques to earthquake prediction, training models on historical data to identify potential precursory signals. Early results are intriguing, but not yet operationally useful. The fundamental problem remains. Earthquakes are rare events, and machine learning performs best when it has large training datasets of the phenomenon you're trying to predict. Even with decades of global seismic data, the number of well-instrumented large earthquakes is limited, making it difficult to train robust predictive models. The future of this field might lie in multidisciplinary integration, combining seismology, electromagnetics, space weather monitoring, satellite remote sensing, and AI analysis into a comprehensive early warning system. Imagine a network that monitors Schumann resonance, ionospheric electron density, ground-based electromagnetic signals, radon emissions, GPS station movements, and space weather conditions in real time, feeding all of this data into machine learning models trained to recognize the subtle multi-parameter signatures that precede major earthquakes. If such signatures exist and are consistent enough, such a system might provide hours or days of warning, enough time to save lives even if it cannot pinpoint the exact magnitude, location, or timing with perfect accuracy. The interstellar object 3I Atlas fits into this cosmic narrative not as a trigger or cause, but as a reminder that Earth exists within a broader cosmic context. The object's journey through the solar system, its interaction with solar radiation and the solar wind, the cometary activity it exhibited as it approached the sun. All of these are natural processes we can observe and study. The object carried information about its origin, the interstellar environment it traveled through, perhaps even the stellar system it was ejected from billions of years ago. Studying interstellar visitors expands our understanding of the cosmos, teaches us about the diversity of small body compositions, and provides ground truth for theories about planetary system formation. The coincidental timing of its passage with electromagnetic anomalies on Earth is just that, coincidence. Our pattern-seeking brains want to connect the dots, to find meaning in simultaneity, but correlation without mechanism is not causation. The Earth's electromagnetic heartbeat is indeed not isolated. It responds to solar activity, to atmospheric dynamics, to ionospheric changes driven by space weather. But extending that connectivity to include gravitational or electromagnetic effects from objects millions of miles away requires extraordinary evidence, and no such evidence exists. Still, the question hovers in the background, philosophical rather than scientific. What if there are connections we haven't yet discovered, couplings between Earth and cosmos operating through physics we don't fully understand? Quantum entanglement connects particles across arbitrary distances. Dark matter and dark energy dominate the universe's mass-energy budget, yet we barely understand them. Gravitational waves ripple through space-time, undetected until 2015, despite being predicted a century earlier. The history of science is a history of discovering that reality is stranger, more interconnected, and more subtle than our intuitions suggest. Maybe Earth's electromagnetic environment is influenced by cosmic factors we haven't yet identified. Or maybe it's not, and we're just telling ourselves stories to make sense of noise. Either way, The cosmos continues its indifferent motion, stars burning, planets orbiting, interstellar objects drifting through the dark. And Earth continues its tectonic dance, plates grinding, stress building, eventually releasing in violent shakes that care nothing for our theories or our fears. The only certainty is that we're watching, measuring, trying to understand, hoping that somewhere in the data is a clue we can use to save lives when the ground decides to move. While electromagnetic anomalies dominate one corner of scientific attention, the broader universe continues to reveal its secrets at an accelerating pace, and few discoveries in recent months have captured imaginations quite like the detailed observations of 3I Atlas, the third confirmed interstellar object ever detected passing through our solar system. This visitor from beyond, this cosmic wanderer that originated in the gravitational embrace of some distant star, arrived with mysteries and left with even more questions than answers. Interstellar objects are vanishingly rare in our experience. The first, 1I Oumuamua, rocketed through the inner solar system in 2017, discovered only as it was already heading back out toward interstellar space. Its elongated shape and slight non-gravitational acceleration sparked debate about whether it was a comet, an asteroid, or something entirely unprecedented. The second, 2I Borisov, arrived in 2019 and behaved much more like a typical comet, with a clear coma and tail driven by sublimating ice as it approached the sun. Or 3I Atlas, discovered in late 2024 and reaching perihelion on December 14, 2025, has proven to be perhaps the most scientifically valuable of the three because we had time to prepare, time to point our best instruments at it, time to gather data that will fuel research for years to come. What makes these objects so scientifically precious is their origin. Everything in our solar system formed from the same primordial cloud of gas and dust that collapsed to create the sun 4.6 billion years ago. Asteroids, comets, planets, they're all our siblings, chemically and physically related through shared heritage. Interstellar objects come from somewhere else entirely. They formed around different stars, condensed from clouds with different chemical compositions, evolved under different thermal and radiation conditions. Studying them is like receiving postcards from alien solar systems, samples we could never reach with spacecraft, but which the universe occasionally delivers to our doorstep. 3I Atlas did not disappoint. As it brightened approaching the sun, telescopes around the world and in space trained their instruments on this visitor. The James Webb Space Telescope, humanity's most powerful infrared observatory, captured spectra revealing the comet's chemical composition with unprecedented detail. Carbon dioxide dominated the emissions, much more so than typical solar system comets, which are usually richer in water ice. This CO2 dominance tells us something profound about the formation environment of this object, suggesting it condensed in a region of its parent stellar system where temperatures were cold enough to freeze carbon dioxide, but perhaps warmer than the outer regions where water ice dominates in our own solar system's comets. Polarimetric observations added another layer of strangeness. Polarimetry measures how light is oriented as it scatters off dust particles in the comet's coma, revealing information about particle size, composition, and structure. The polarization signature of 3I Atlas showed unusual features that don't quite match typical comet dust, hinting at either a different mineralogical composition or a different size distribution of particles. These are subtle clues, details that require careful analysis and comparison with models, but they point toward the fundamental truth that not all comets are created equal, and that interstellar space contains diversity we're only beginning to sample. Perhaps the most visually striking discovery was the wobbling jet structure in the comet's anti-tail. Most people imagine comet tails pointing away from the sun, driven by solar wind and radiation pressure, pushing gas and dust outward. This is correct for the primary dust and ion tails, but under certain geometric conditions, a comet can also display an anti-tail, an illusion created when Earth passes through or near the comet's orbital plane. From our perspective, we see dust particles that have been left behind along the comet's orbit, creating a tail that appears to point toward the sun. It's not actually pointing sunward. It's an artifact of viewing geometry, but it's spectacular when it occurs. 3I Atlas's anti-tail showed structure, patterns that suggested the comet's nucleus was rotating and emitting jets of material in preferred directions. As the nucleus spun, these jets created a wobbling, spiraling pattern in the released dust, visible in high-resolution images as wave-like structures propagating through the tail. This is not entirely unusual for comets. Many showed jet activity driven by active regions on their irregularly shaped nuclei. What made it notable here was the quality of the observations and what they revealed about the nucleus's rotation state and activity distribution. The object was tumbling, rotating in a complex manner that suggested it might be irregularly shaped or composed of multiple smaller bodies loosely bound together. The closest approach to Earth occurred on December 19th at approximately 1.8 astronomical units, about 167 million miles. This is not close by any meaningful standard. The Moon orbits Earth at roughly 240,000 miles. Mars at its closest approach comes within about 35 million miles. Venus can approach within about 25 million miles. 3I Atlas never came anywhere near threatening Earth, and gravitational effects from such a small object at that distance are utterly negligible, far weaker than the gravitational influences we experience from our planetary neighbors on a daily basis. Yet the timing, as noted earlier, has fueled speculation. An interstellar visitor passing through the inner solar system, electromagnetic anomalies on Earth, a potential earthquake window opening. The human mind sees these events occurring in close temporal proximity and wants them to be connected, wants there to be a cosmic narrative where everything matters and nothing is coincidence. The scientific reality is that space is vast, distances are enormous, and the physical effects of a small icy body millions of miles away are vanishingly small compared to the constant barrage of solar wind, the gravitational tug of the moon, and the internal dynamics of Earth's own systems. What studying 3I Atlas does provide is insight into the diversity of planetary systems. Every interstellar object that passes through our solar system carries information about conditions elsewhere in the galaxy. The chemical composition tells us about the star it formed around, the temperature and pressure conditions in that protoplanetary disk. The rotation state and structural integrity tell us about collisional processes and gravitational interactions that shaped its evolution. The activity level and outgassing behavior tell us about the balance of volatile ices preserved over potentially billions of years of interstellar travel. From a broader astronomical perspective, these objects remind us that the galaxy is full of debris, material ejected from planetary systems through gravitational interactions, planetary migration, and close stellar encounters. Estimates suggest that trillions upon trillions of rogue planets, comets, and asteroids drift through interstellar space, untethered from any star, wandering in the dark between stellar systems. Occasionally, purely by chance, one of these wanderers passes close enough to our sun to be detected and studied. We're fortunate to live in an era where our telescopes are sensitive enough to catch them. The lesson from 3I Atlas and its predecessors is that the universe delivers surprises if you watch carefully enough. Each interstellar object has defied expectations in some way, revealed properties that don't quite match our assumptions based on solar system comets and asteroids. This is exactly what science hopes for, not confirmation of what we already believe, but data that challenges our models and forces us to refine our understanding. The cosmos is not required to conform to our theories. Our theories are required to conform to the cosmos, and when they don't, we change the theories. Meanwhile, back on Earth, the electromagnetic anomalies, continue or don't, the seismic risk remains or diminishes, and life goes on with or without cosmic connections. The universe spins on, indifferent to our need for meaning, beautiful in its complexity, terrifying in its scale, and endlessly fascinating to those willing to look up and wonder what else is out there, waiting to be discovered.